All right, in the diagram, AE is a tangent. AE is a tangent to a circle ABCD, right? So here is the line that they are talking about, that it is a tangent at A. So should you are given the line that is a tangent, you have to remember the theorems around this line, which is the tangent, right? You have to think about the tan chord theorem, which has to be obvious. You have to think about the radius or the diameter that is always perpendicular to the tangent at the point of intersection. You have to also think about, you can be given two tangents that are from the same point outside the circle, that also going to give you some bit of information. So you have to think broadly when you are given the tangent. So here we have a tangent at A. Then AC is a tangent to a circle CDFG at C. So we can see that AC is also a tangent over there of the smallest circle, So also think about the tan chord theorem, and everything else that is given is going to give you the information. Now we also have CE and AG intersect at G. So we have CE and AG, they actually intersect at D. So we just have this information now to work on. So what is the question now? The question says, if A1 is equal to X, and this is A1 which is equal to X, and E1 is equal to Y, this is our E1 that is equal to Y. So we have to prove the following with reasons. The first proof that we need to do is prove that BCG is parallel to AE. BCG is parallel to AE. So this is the line that you need to prove it parallel to AE. So this BCG, we need to prove it is parallel to AE, just like that. So one other thing that you need to remember about proving parallel lines is actually the properties of a parallel line. Right? So we just need to prove the properties of a parallel line. If you're not given the parallel lines, use the properties of a parallel lines to prove that this is whether the lines are parallel or not parallel. For example, for parallel lines, we know that corresponding angles are equal to each other, right? Corresponding angles are equal to each other. If you have any alternate angles are equal to each other, so you just need to find a way to actually find the positions of these alternate angles. For example, if we can start with number 1, just make some indications to see that for these lines to be parallel to each other, the idea is to prove that G2 and A1, since they are alternating, you just have to prove that they are also equal to each other. So if there are angles that are alternating and also found equal, then therefore they are subtended by parallel lines. Therefore, these lines are going to be parallel to each other. So if G2 is found being equal to A1, which is X, then therefore these lines are parallel to each other. Or one may think of using this information, this angle and this angle, provided that this CA is viewed to be a transversal line, or since we have this one and that one as another option, which means we have viewed that GA is a transversal line, just like that, so that we have amakwapaka Z. We used to do that. You say that. So we have that. Or maybe you see tray is found equal to Y, which is that E1, since this is going to be viewed as amakwapa in the what transversal line, then therefore these lines will be parallel to each other. So now we can see that we have more information about alternate angles, that we need to prove that they are equal to each other for these lines to be parallel. So let's begin now. How do we prove that A1 is equal to G2? It is with understanding that what you call, since we have the tangent E1 now, we have the tangent EA right there, right? Then this is the tangent EA, and in this tangent we can see that there is a chord DA over there, and these two lines, they are forming this angle, right? So this is the angle between the tangent and the chord. What do we know about that? We know that this angle that is between the tangent and the chord, it is equal to the angle subtended by the very same chord at the circumference of the circle. So if you can just view that this chord is subtending this angle C2 at the circumference of the circle, this is a chord is subtending that angle, which is C2 is also going to be equal to x, because this is the angle between the tangent and the chord. It is equal to the angle subtended by the very same chord at the alternate segment of the circle. So now we can just practically write it down that C2, angle C2 is now going to be equal to x, right? Which is equal to A1. So we just need to tell where is this x from, right? So we have this. So the reason is tan chord theorem. This is tan chord theorem, right? So now, after having all this information about this site, you can also view that this CA, right? This CA is a tangent of the smaller circle, and also there is this chord over there. All right, so this is the angle between the tangent and the chord. So it is basically going to be equal to the angle that is subtended by the same chord at the circumference of the small circle. So that you'll find now that G2 is equal to C2. They are both equal to x. Then the reason is the same. All right. So we can see. Therefore, we can see that G2 is equal to A1, right? They are both equal to x, because we wanted to prove that actually this is also equal to x if this is x, right? So that these alternate angles, should they be equal, then these lines are parallel to each other, right? So we have that information now, that therefore what GCB is actually parallel to EA. The reason for that, we can see that the alternate angles are equal. Otherwise, if the alternate angles were not equal, then these lines were not going to be parallel to each other. Then, because alternate angles are equal, right? So should the alternate angles are equal, then therefore this is just the converse law of parallel lines. Then we are done for the first question. We proved that this line is parallel to the other one. So we can just use this information here for future calculations, right? So I hope you will take this one down, because I'm about to open the space for the second question now. Well, now, after having all that, we can just indicate the fact that these lines are now parallel to each other, so that we can use everything else that has to do with these parallel lines. So this one is x, this one is x as well. We just don't have to get rid of this information, because it is very useful. We are not going to redo it in the second question, because it's already been done. We found it, everything. Number 2, we are to prove that AE is actually a tangent to a circle FED. We are to prove that the line AE, let me just change the color. We have to prove that the line AE, this line, is a tangent to a circle that will pass through F, D, and E. I'm sorry for my circle that is not cyclic, but Anyway, you get the idea that if this is a tangent, if you are proving that AE is a tangent, so when you're proving that AE is a tangent, you need to know that this line and this chord over here, this line that you don't know whether it's a tangent, and this chord over here called DE, they are subtending the angle Y, right? They're subtending the angle Y over there, right? Should that angle Y be equal to the angle subtended by the chord at the circumference of this new circle now, which means if F1 is found equal to Y, then this line is going to be a tangent of this circle, right? So we just need to find, okay, if for the line to be a tangent, the angle between that line and the chord must be equal to the angle subtended by that chord at the circumference of the circle. So this is the chord DE. It must subtend the angle that is equal to Y, which is between this line and this chord, right? So we need now to prove that F1 is actually equal to Y as well. Okay, now how do you go about doing this thing, Kengoku? Well, what are we having? We have Y being equal to that, and we also know that we know the fact that what you call, yeah, we know that this line is parallel to this line. That information we know, right? So these lines are parallel to each other, and that makes C3. Can you see C3? C3 is equal to E1. The reason for this, these are alternate angles, right? These are the alternate angles because of lines that are parallel to each other. So I think we can just write that down, because I think it's going to give us information about these 5 marks. We are proving that AE is actually a tangent of what? Of this, of that. So this is X, remember? Then this is Y. Now, what do we do? We have C3. C3, which is found equal to E1. They are both equal to Y. Reason. These are alternate angles because you can see that Z and the Ziligan J, it's because these lines are parallel to each other. So then alternate angles are equal, right? Because with GB, I can just say GB is parallel to EA. So we know that this C3 is also equal to Y. Then let's check the information about F1. How can F1 be equal to C3? Well, everyone can know that can see that if this F1 is actually the exterior angle of this cyclic quadrilateral over here. Well, so this F1 is actually the exterior angle if we can extend the line over there. Okay, this F1 is going to be equal to Y as well. So we can see that we also have this Y over there, that we can say F1 is actually equal to C3. They are both equal to Y. Reason this is the exterior angle of a quadrilateral. Of a what? Of a cyclic quadrilateral. Of a cyclic quadrilateral. So we have that. So therefore, F1 is now equal to E1. E1, E1, they are both equal to Y, right? We did prove that. You can just say proved, because they are all equal to Y. So you can say that, therefore, AE or EA is actually a tangent. is actually tangent to that circle. Reason, it's because of converse. We didn't have tangent. We are using converse of tan chord theorem, right? So that is the converse of tan chord theorem. So we managed to prove that f1 is basically equal to the angle subtended by this line and the chord, right? So which means this line is a tangent. Should it be equal, should the angle subtended by it and the chord equal to the angle subtended by that chord at the circumference of this imaginary circle, then therefore that makes this line to be a tangent. Okay, so let's check the last question. The last question says prove that AB is actually equal to AC. Let me just get rid of this other information of them. Let's prove that AB is actually equal to AC. That can only be possible if we prove that C1 is equal to that B, so that if these angles are equal, they have to be facing equal sides as well, right? So we need to prove that C1 is actually equal to that B. So if you're taking note, I'm taking this information out now so that I open some space. Here you go. Well, so we have this information. So how do we then, because to find AB equal to AC, it is when we C1 being equal to that. If these angles are equal to each other, then these lines will be also equal to each other. So the base angles of this isosceles triangle, if it was given to be an isosceles triangle. So how can they be equal? First thing, we can see that the tangent that we have over here, let me just use this one, probably this one. The tangent that we have here, we can still use it because it can give us the information, but because the tangent and this chord over here, right? The tangent and this chord over here have to give us the angle bani. Let's say this angle is angle CAE. Angle CAE. Angle CAE is this angle that is between this tangent and this chord, right? So angle CAE must be equal to, or is equal to, angle B, right? Reason, it's a tan chord theorem, right? It's a tan chord theorem. This angle must be equal to that angle, right? Because this is the angle between the tangent and the chord, it must be equal to the angle that is opposite to that chord at the circumference of the circle, right? Now this is what we have. This is tan chord theorem, right? But we can tell that this angle C1 is equal to this angle as well. Why so? Because this line is parallel to that line, so these alternate angles have to be equal to each other. So C1 is now equal to angle CAE, raising alternate angles. Alternate angles. Why? Because CB is parallel to AE, right? So then therefore AB is now equal to CA, and the reason is that the well, the angles and the equal angles have to face, okay, equal angles, let's say equal angles must face, must be opposite, must face equal sides. So if these angles are equal to each other, they must be opposite equal sides. So we are done with that one, and that is just 4 marks, right? So it is basically that. So when you are given all these things, you just need to find a way to figure out the information. Right. Then we are done.